Hey guys, and I want to talk about force problems involving multiple objects. Let's check it out. So the big thing to know, the big thing to remember is that objects that are connected, two objects acting as a system, will have the same velocity and the same acceleration. If two or more objects are connected as a system and they move together, they have to have the same velocity and they have to have the same acceleration. Otherwise, they would be getting closer or farther apart from each other. But instead of calling these velocities, let's say for two objects, v1 and v2, that's two variables, I'm just going to call it v because it's the same, so I have instead one variable. Same thing with a. Instead of calling it a1 and a2, I'm just going to call it a because it's the same. That way I have one variable, not two variables. Okay? The way to solve this is very similar to what we've been doing with problems of just one object. We're going to draw a complete picture, and very often you get that already drawn out for you. And then for each object, you're going to do this as many times as you have objects. You're going to draw the free body diagram. Free body diagram. Remember, this is your FBD. You're going to write for each object, sum of all forces equals ma, and you're going to solve. So if you have three objects, you're going to draw three diagrams. You're going to write F equals ma 3 times and combine those equations. These are the same exact steps as you would do for one object. It's just that if you have two objects, you do that twice, one for each. Okay, so let's try this example here. Two blocks, masses 2 and 3, are initially at rest on a horizontal frictionless surface connected to each other by a light string. So there's a string here, so there's a tension. You pull horizontally on the 3, so this is your pull right there on the 3, with a force of F equals 15 newtons. It's a constant force. And I want to calculate the system's acceleration and the tension between the two blocks. Okay? So I want to know what is A, that the entire system will have. Remember, A1 and A2 are the same thing, so I can just call them A. And I want to know what that A is. And I want to know what is the tension between the two right here. Okay, now I have two objects, and where do I start? My tip here, pro tip number 1, is that you're going to begin with the simplest object. Now, what do I mean by simplest? You want the object that has the least amount of forces acting on it, and it's usually the object that is at the ends of the problem, okay, or at the edge of the problem. And in this case, it would be object number 2. Let me show you real quick. Object number 2 has tension pulling to the right. Object 3 has tension pulling it to the left. By the way, these two tensions are the same because it's the same string. And it has this F here. So you can see this guy has two forces on it. This guy only has one force on it. So I'm going to start with this because it's simpler. Okay? So sum of all forces equals ma. Let me draw the free body diagram. This is not a free body diagram. Free body diagram would look like this. This is a free body diagram for the 2. And the 3 is like this. Okay, so the sum of all forces on the 2 equals the mass of the 2 and the acceleration of the second block, of the 2 kilogram block. But all the accelerations are the same, so I can just call this A. I can do the same for the third object. Sum of all forces on 3 is the mass of 3 and the acceleration of 3, which is just A. So 2 has only one force on it, so that force is T going to the right, so I'm going to call this plus T. Mass 2 is 2 kilograms, that's why we called it M2, because it was 2 kilograms. And acceleration, you could have called it M1, M2 if you wanted. So that's it, there's nothing else I can do here. And notice that I'm stuck. I don't know T and I don't know A. So let's continue here with this next block. You're supposed to get stuck. You're supposed to not know this until you write all the equations. So this block has T to the left, negative T, and F to the right. Mass is 3, and acceleration I don't have. I'm going to move some things around here. So this is F is 15 minus T equals 3A. Again, notice that just like here, I had one equation, two unknowns. Here I also have one equation, two unknowns. But they're the same two unknowns. So now I have two equations with the same two unknowns. It's called a system of equations, and I can solve this. Now, the way you probably are used to doing this is you can, let's say, I can plug in 2a for this t over here, It'd be negative 2a because it's a negative t. And then I would be able to solve for a, right? So I can isolate one variable in one equation, plug it into the other, and all that. But for these problems, you're always going to be able to add the two equations, and that's what I want to show you. So I'm going to get this equation right here and stack it up over here and add it to the first equation. Now, every time you do this, the tensions are going to cancel because all the tensions are doing is holding this thing together. So the tensions will cancel. And the way you do this, by the way, is you add everything that's on the left together. So all I get here is a 15. That's why the t's cancel, because I was combining them. And then you add everything on the right together. That's going to give me a 5a. Okay, so you're always going to be able to do that. And this gives me a equals 15 over 5, 3. Once I have that, to find t, so that's part A is 3. Once I have that, to find t, I just have to plug a back in there, right? So I just plug a back over there, and I know that t equals 2a, so it's 2, 3, 6 newtons. All right, so that's the final answer for these two. So you're always going to be able to add up the equations. Even if you had 3 objects, 4 objects, you're always going to be able to add it up. So let me show you a way that you can do this a little bit easier, even simpler than this, right? You can combine objects to find the acceleration. If you look at this, you're pulling with 15 on the 3, but the 2 is connected to it. So if you think about it, you're really pulling 5 kilograms total of mass, right? So I could combine the objects to find the acceleration. So instead of a 2 and a 3, I'm just going to say I'm pulling on a 5. And with a force of 15. Now this just got a whole lot easier. I can just write sum of all forces equals ma. There's a single object. The force is a 15. And mass is a 5. So the acceleration is a 3. And I did that in 3 lines instead of however many these took. The problem with this is that I cannot do this. I can no longer find t once I do this, at least not with this diagram. And the reason is, since I merged these objects here, t is kind of like in here somewhere, right? It's now an internal force. You wouldn't be able to see t. It doesn't exist anymore, basically. So to be able to solve for t, I'm going to have to go back to one of these 2 original diagrams, right? And I'm going to pick the simplest of the 2. Tension is touching the 2 kilogram and the 3 kilogram. They both have tension on them. So I can just pick one of the 2 of them. I'm going to pick the the 2 kilogram because it's the simplest one, right? So I'm going to say, here's a 2 kilogram. It's being pulled by t. And I'm going to say sum of all forces on the 2 is the mass of the 2a. And the force is the tension positive. The mass is 2 kilograms. And the acceleration I just got over here is a 6 newtons. So this whole question got solved in 5 lines, 2 of which are just F equals ma. Okay, so you can combine things, but then once you find the acceleration, you're gonna have to write the F equals ma for individual objects and plug your acceleration there. Okay, so that's what happens when you have 2 objects that are connected together. Now, a setup very similar to that applies also to these 2 other situations here. When you have a mass inside another mass. So a mass moves with another mass inside, like a passenger in a car. So imagine that this is a car right here. It's a really crappy car. And there is a seat. And it's terrible. And you're sitting on the seat. Okay, I hope you can draw better than that. And then the other situations, if you have 2 objects stacked up on top of each other, little m and big M. Okay, so the idea is there's let's say the passenger is little m, the car is big M. The idea is there's a force that the engine applies on the car, or maybe it's a cable that's pulling the car, whatever, and that force equals to, it's the force on the car, so it's the mass of the car and the acceleration of the whole system. There's also a force that's applied on the driver. Okay, the force of the seat on the driver. When you're in a car, the reason why you go forward with the car is that the seat pushes you forward because the seat is fixed to the car. And this would be mass of the driver because it's the force on the driver and acceleration. And these two accelerations are the same. The forces aren't, but the accelerations are. And by the way, when you do this, you can combine this whole thing as just one object, and you could use this to be the total mass of both. So I'm just kind of explaining this. We're actually going to work out this problem in example 2, but for now I'm just giving you a brief look. Here, let's say I push here with an I pull here with an F pull of whatever that is. That F pull is going to be MA. Now, if this object on top moves with the object in the bottom, it's because there's some friction here, and we'll do this later. But just conceptually, if they're both accelerating to the right together, they both need a force. This guy is being pulled on. This guy is somehow, again, we'll talk about this later, being pushed as well. So F of little m on little m is little m acceleration, and the accelerations are the same because they move together. So again, we'll do this later when we deal with friction. But for now, let's look at this guy inside of the car. So it says, when a 2940 Newton force accelerates a 900 kilogram car, how hard is the seat push on an 80 kilogram driver? So I'm going to draw a simpler version of this. Here's the car, mass big M, and this guy's here in the back of the car being pushed forward, little m. And the force that's pulling the car, or pushing the car forward, doesn't matter, is 2940 newtons. All right, and I want to know how hard is the seat pushing on the driver. So this is going to cause some sort of acceleration to the car, and the driver is also going to have that acceleration. So I want to know the force that the seat pushes on the driver. So I want to know, since it's on the driver, sum of all forces on the driver is mass of the driver, which is little m, and A. The only force on the driver here is the force of the seat on driver, which is what I want to calculate. His mass is 80, and the acceleration I don't have, so I'm stuck. But guess what? This acceleration is going to be acceleration of the car. Acceleration of driver is the same as the acceleration of the car. So I can go back here and try to figure out the acceleration of the car. Now this force, 2940, is pulling both the car and the guy, the driver, right? So the driver is inside of the car. It's all one big system. So I can write that this one force, sum of all forces on the system, is the mass of the system and the acceleration of the system, which is just A. The force is 2940. The mass is 900 plus 80, A. And if you move everything around here, you get that A equals 3 meters per second squared, which I can now plug back in here. In 80 times 3, the guy is being pushed forward with 240 newtons. So the big thing to remember here, guys, is that whenever you accelerate, whether you're getting faster or slower, whenever your velocity is changing, there has to be a force acting on you. And if two objects are connected, then they have to accelerate together. Very often you're going to have to find the acceleration of one and plug it back into the other to be able to solve for what you're looking for. All right, so that's it for this one. If you have any questions, let me know.